Going to look at Maxwell Boltzmann distribution curves. And for this, you're showing the spread of kinetic energy compared to the particles of a sample of a gas at a given temperature. And the curve looks something like this. We've got number of molecules on the y-axis and kinetic energy on the x-axis. And indeed, you could have the probability distribution function instead of number of molecules, but a number of molecules is almost a more straightforward way of looking at things. The red line there is the pointer of the kinetic energy where to the right of it, the smaller portion, to the right, those molecules will have sufficient kinetic energy to actually react. That's the activation energy line. So relatively few particles are going to have that amount of energy. Just circled 2 here and showing really that small number of molecules have very low energy and a small number of the molecules have high energy. And then we're going to look at the apex at the peak, and that's the most probable energy. So most of the particles will be relatively close to that probable kinetic energy, with the largest fraction of molecules having this kinetic energy at any given instant. And so we've shaded the particles to the right where they have the required activation energy, and the curve is asymmetrical around the maximum value. The area under the curve gives the total number of molecules. And so both these curves here are representing distribution curves under different conditions at different times. But for these two, they represent the same number of particles. And the curves were produced with the lower temperature having the higher apex, the higher temperature having the lower apex. But it's not the apices that is really the significant factor here. What you're looking at is the higher temperature actually has the larger number of particles with the kinetic energy above the activation energy. And what does temperature do? Gives particles more speed, so they are indeed going to have higher kinetic energy and more likely to have the activation energy than at a lower temperature. And so that's just the straightforward curve. And a reminder here as you're looking at them and maybe asked to draw one, that the curve doesn't cross the x-axis, sort of an asymptote as it's going across there. And we're just pointing down here to the EA activation energy line, and the red portion is the number of particles that have the required activation energy. And a reminder that it's a small portion. And what we're doing here, the red portion is the same as the previous one. We're adding a catalyst. And what does a catalyst do? It lowers the activation energy. So the vertical line here is the new activation energy with the catalyst. So there's all these particles here in blue that have now got more than the activation energy. So there will be more successful collisions, more reactions for the given reaction. And then we've got here 3 possible scenarios of different temperatures, and the one with the lowest apex is going to have the highest temperature and the highest number of particles that are going to be to the right of the activation energy line. And a little bit of a summary. So you can look at distribution curves at reactions at different temperatures to compare them. The higher temperature curve shifts more to the right. The higher temperature curve has a lower peak. The area under the curve, the number of particles, is going to be the same. And the end of the higher temperature curve is above the curve of a lower temperature. Even though the apices, the highest point of the graph, it's the other way around, with the lower temperature having the biggest peak, the biggest Y value. And a higher temperature curve doesn't meet the x-axis, the lower temperature curve doesn't either. None of them do.